f of x is equal to 1/3 x squared plus 4 over x squared minus 2x minus 1, where x is greater than 0. Part A, show that the equation f of x equals 0 has a root alpha in the interval between 6 and 7. So I'm first going to substitute 6 into my function. So that's going to be 1/3 times 6 squared plus 4 over 6 squared minus 2 times 6 minus 1, which gives me minus 0.8 reoccurring, so a negative. I'm now going to substitute 7 into the function. So 1/3 times 7 squared plus 4 over 7 squared minus 2 times 7 minus 1, which gives 1.414, which is a positive number. So we have a sign change. So I can now write the usual sentence, sign change in the continuous function so there must be a root in the interval between 6 and 7. Part B. Taking 6 as a first approximation to alpha, apply the Newton-Raphson process once to f of x to obtain a second approximation to alpha. Give your answer to 2 decimal places. So the Newton-Raphson process is xn plus 1 equals xn minus f of xn over f dash of xn. You do get given that in your formula booklet. So we are going to need to find f dash. We need to differentiate our function. So let's do that up here. In order to differentiate the function, I need to think of this x squared. I need to get rid of that off the denominator. So I'm going to rewrite that like that. Now I can differentiate this. The 1/3 x squared is going to become 2/3 x to the power 1. The 4x to the power minus 2 is going to become minus 8 x to the minus 3. And the minus 2x is going to become minus 2. And the minus 1 will differentiate to be 0. Right, I have everything I need now. So to get my second approximation, I'm going to do my first approximation, 6, minus f of 6 divided by f dash of 6. So if I substitute 6 into my original function, so substitute 6 into this, I get the minus 0.8 reoccurring. If I now substitute 6 into my gradient function, so substitute 6 into this, I get 1.9629, and then doing this calculation, the 6 minus 0.8 recurring over 1.9629, I get to 2 decimal places 6.45, and so that is my second approximation.